Alright, let's take a look at section 2.3. We're starting out with just some basic transformations here of our x to the third and x to the fourth parent functions. So remember, these are just monomials because as of right now it's a single term. So we're going to do some transformations on these. So let's get the basics in there for the parent functions first. As far as x to the third, we know that's just like our S-shape type of a function. But let's put in some real numbers so that when we do our transformation, we can actually transform real values here. So if I put -1 to the third, it's still -1. 0 to the third is still 0. 1 to the third is still 1. So just keep in mind, I know this looks like a linear function. If we just plot those 3 points, it looks like a linear function, but if we plot more points, the more curvy it would get. So we're just going to go off of those 3 for now and at least build the basic parent function. And we're going to do a little transformation here. So don't look at the next page yet. I want to do this with you before we look at what the outcome is supposed to be. So for this, we know this is going to go to the right one. We know this is our vertical stretch of 2. So remember, as far as order of operations, we talked about shy 15 in an earlier video. And so we always want to make sure we're sticking with that. So our stretches come first, stretch and shrink goes first, and then we would do the horizontal shift. Now in this case, the horizontal shift affects us to the left and to the right. A vertical stretch only affects the y values, so really the order wouldn't matter for this because one affects the y's and the other affects the x's. So we're just going to do them both at the same time. And I have kind of a little bit of space here, so I'm not going to write out every step of this. Typically I would kind of show you the next set of points and I would write out another T-chart so you could see the numbers, but let's just talk our way through this one. So my horizontal shift means I'm going to add 1 to my x's, and this means I'm going to multiply the y values by 2. So if I add 1 to this, it becomes 0. Multiply this by 2, I get -2. So 0, -2 should be one of my new points. If we do this to 0, 0, the horizontal shift means I'm going to add 1 to this, but when I multiply this by 2, it's still 0. So 1, 0 should be another point on the graph. And then on these guys, add 1 to this, multiply this by 2, it should become 2, 2. And so you can see it's getting a little skinnier here because of the vertical stretch, and we shifted over to the right. So it should be a little skinnier and the whole thing should get shifted to the right. So it should look something like that. So we should be able to do that without a graphing calculator. We're just going to throw it in so we can take a look at it. So we started out with x to the third, so let's throw that in. And then we had our 2x minus 1 to the third. So we're going to graph them both. So here comes the parent function, and here comes the new one. There you go. So, and we can even confirm by looking at the table, make sure our points are in that table. So if I go to my table, we said we had 0, -2, and that's on there. That's the red one. We had 1, 0, and 1, 0 you can see is in there. And then we also had 2, 2, which is in there as well for the red graph. So the blue one was the parent function. The red one is for the new one. And so we're good to go. Let's try that with our x to the fourth as well. So for x to the fourth parent function, again, let's just throw in a couple numbers here, so we can transform some real values. So to the fourth power would give us these outcomes. We talked about this in an earlier video, but basically x to the fourth is just like a parabola, only not quite as curvy. It's a little more squished. And so I've showed you this before, but I want you to see it side by side here. So if our typical parabola, obviously x squared, and let's graph x to the fourth as well, because I want you to see them side by side. They're not the same graph. So I want you to see them together here. So there's the parabola, and you can see the red graph that's going to come up is going to be x to the fourth, and you can see it's obviously much narrower, and down here it's like squished. So I'm going to zoom in on that so you can see it. So if I zoom in on that, you're going to see how the red one is kind of it's steeper slope, but as it gets to the bottom, it's like flat almost. So you can see it's like kind of flattening out down there. So that's really what's going on with this guy. So pretty narrow, and then it goes pretty flat, and then back up. So it would look something like this. Okay, so what if we do all three of those? So we have a reflection. It's not attached to x because it's outside of the parentheses, which means it's going to reflect up and down across the x-axis. We are going to shift left 1 and down 2. If we kind of put all those in, so reflect across the x-axis is this guy. So here's our reflection. We're going to go left 1. That's the horizontal. So left 1. This is our reflection. And then we're going to go down 2. That's our vertical shift. So down 2. I'm abbreviating so I can fit it on my page. So you can see the order we need to do this in. So we're going to go left 1. I'm going to reflect and do a vertical right there. So if you look at the order of what's going on here, which ones would be affected, or which ones do the order really matter for, right? So the horizontal shift is going to affect the x's, but these guys are both going up and down. So this is where the order really matters, right? So I got a reflection as well as the vertical shift. These guys affect me up and down. I got to make sure I do these in the right order. He is really separate from those, right? And so I could really do this sort of at any time here. So anyway, let's take these. And I'm sort of breaking my own rule by not showing all my work. But I have sort of limited space here. So here we go. So if I go left 1, that means all of these are going to subtract 1. So it's going to become those numbers. The reflection, remember, would change the sign of your y coordinate. And then it's going to go down 2. So the idea is we change the sign of the y coordinate. Essentially, you could say you're multiplying it by -1. Okay, so I'm going to multiply my y coordinate by -1, and then I'm going to subtract 2. So if I multiply this by -1, it becomes -1, and then subtract 2, times -1, subtract 2, times -1, subtract 2, and we're getting this look here. Okay, so if I plot those points, I got -2, -3, -1, -2, and 0, -3. And again, you'll notice on this one, it's the same width because all we had out front was a reflection, not a stretch or shrink, right? And so it should take on the same shape as this, but it was shifted and reflected. Pardon the ugliness of my drawing, but you get the idea. So if we did throw that in, so we have our x to the fourth. I always like to check answers this way. Make sure everything looks okay. So negative x plus 1 to the fourth minus 2. So it should look like this. Let me get my window back to the normal settings. Actually, I'm going to go -5 because this one's not that wide. So we'll get a better look at it this way. So the parent function is on top, and then down here should come the one that we did as our transformation. And I should have made that a little flatter, like we talked about earlier. That would have been good. But you can see it does pass through 0, -3, just like we said it would. So I know my points are on the right track with what we're looking at. All right, so let's keep moving here. These, by the way, is they're sort of showing you the steps. I did it all in one step. They did the reflection first and then the transformation. We still got the same result, which was this guy. And I like doing it with real numbers anyway, so I kind of prefer you to do it that way. right, so a couple things we're going to talk about here with some things that I want to show you in the book. So I'm going to switch over to that real quick. So I wanted you to see, as far as the cubic functions are concerned, I do want you to keep in mind sometimes they can be sort of this very skinny S shape, all the way to a very dramatic S shape, right? So if you looked at this one is increasing forever, right? There was no change in slope. It is always increasing. This one, however, goes from increasing to decreasing to increasing in a very extreme way. And then of course we have the negative ones as well. So if you get a reflection, they're going to do something like this. And so again, you can get sort of a very narrow one where it maybe is like decreasing, and then it might even flatten out to a zero slope and then decrease again, or it could go decreasing, increasing, and decreasing. And so in these cases, you may have what we call relative extrema, which are your maxes and mins, which we've already talked about. Of course, you can also get cases where there aren't any, right? This one doesn't have any relative maxes or mins. Its minimum is negative infinity and maximum is positive infinity, and there's never a change from increasing to decreasing. So these can really vary quite a bit. The same thing is true with x to the fourth graphs. We just looked at this one. But again, these can take on a much more dramatic shape as well. So there's a theorem here that they want you to be aware of. When you have a polynomial function of degree n, so n represents the exponent, right? So if it's a, say, fourth degree, so a fourth power graph, which are these, then you can have at most n minus 1 local extrema. So in other words, if my graph is x to the fourth, then I can have at most 3 maxes or mins, as well as at most n zeros, which are your x-intercepts. So this was something you did in Algebra 2. So if it's x to the fourth power, then I can have at most 4 x-intercepts, is what they're telling us on this. So that's something we got to keep in mind. I wanted you guys to see those. I also wanted to talk about when you graph, how do I know if something passes through the x-axis versus like bounces off of it with something like this. And so I wanted you to see a figure on a later page. So let me scroll over a couple pages to 185. This is handy graphing knowledge here. All right, so take a look at this graph right here. So you see how there are 2 zeros. There are 2 x-intercepts. There's one right here. There's another one right here. You'll notice in one case, the graph bounces off of the x-intercept and goes back down. And in another case, it crosses over the x-intercept and continues upward. So how do we know when it bounces or when it crosses? Real simple. When you are looking at a function, so here's just a good example. So if you guys can see this one right here. So when I'm looking at a function like this, you notice how one factor is is to a third power, an odd exponent, and another one is to an even exponent. Well, your odd exponents, it will cross over the x-axis, and on your even exponents, it will bounce off of the x-axis. So if we set this equal to 0, I know that my zeros, or my x-intercepts, are at -2 and +1. Right? So if you look at the graph, here is one at -2, the other is at +1, and you'll notice at -2, it crosses over the x-axis because it has an odd power. So I know this one would have to cross through the x-axis, compared to this guy at +1, it bounced because it's an even exponent. So at +1, it did a bounce and went back up. Right? And so that's just based on whether the exponent is odd or even. The other thing to keep in mind on these is we already know n behavior. If you put all these exponents together, this is an x to the 5th graph. It's an odd power graph, which means in an odd power, one side of your graph should be headed downward, one side of your graph should be headed upward. If the leading term, and this is all stuff you learned last year in Algebra 2, if the leading term is positive, like this is positive right here, I know the right side should end going upward, which means the left side should be going downward, right, in a case like this. So all things I wanted to remind you guys of. So if we go back to our notes here, so just a reminder on these guys is how we find those intercepts, and I know you guys remember everything you ever learned in Algebra 2, so this will be easy. Just kidding, I don't expect that, but I think this will look familiar. So if we're going to find the zeros or the x-intercepts of the graph, same thing. We always do that by setting the function equal to 0 and solving for x. So this is the way that we would do it by hand. So we're factoring, took out the greatest common factor, and then factored one more time to get this. So you can see our zeros would be at 0, positive 2, negative 3. And you can see that represented on the graph as well. So that's how we find our intercepts. So just keep in mind from here, like we were just talking about, if you wanted to graph this function, right, the way we would graph it is we would say, well, this is a cubic function because it's x to the third. It's positive, so I know the right side of the graph needs to be headed towards positive infinity. And so I would simply fit my curve through these three intercepts. As we just talked about, these are all odd powers. X to the first, this is a first power, and this is a first power, which means in all three of those places, I should be passing through or crossing over the x-intercept. And so here's an example of a sketch for what that would look like. So it really wouldn't be all that tough to graph with that information from here. So just a reminder on those. Let me flip. We'll do a few graphs here, and then we'll call it good. So again, now sketching the graph for something like this. Again, we can see that this is technically an x to the fifth if I combine my powers. So with an x to the fifth being an odd powered graph, I know one side should be headed downward, I know the other side should be headed upward, and because the leading term right here is technically positive, I know the right side should be headed up. As I look at these, I can see that at -1, I should be crossing over the x-axis, and at +2, I should be bouncing off the x-axis. And so you see that taking place right here. We had a cross. This one is a bounce. So here is one last piece of the puzzle. What about this little curvy piece right there? Like, how would we have known to draw that? If we just went through the information that I just talked about, why wouldn't it just go more of a flat up and then down and then up? How would we have known to make that little curve? So understand that if you look at these factors, this represents a portion of the graph and this represents a portion of the graph. At -1, this is a cubic function, right? It's an S-shaped graph. So at -1, I should be drawing a cubic function, not just like a straight curve. It should be a cubic curve. It should be an S shape. So at -1, we are drawing this S-shaped graph right there, right? So you can see that S-shaped graph. And then if you look at this portion of the graph, well, at +2, it's a squared function. And you know squared functions are parabolas. So at -2, or at +2, sorry, see the parabola that we have going on right here? So keep in mind what you've already learned, because they still apply to this. So again, when I'm graphing, I'm taking into account that at -1, this is a cubic function, and at +2, this is a quadratic function. And so I still want to fit my graph to model what I know those type of functions look like. And so that's what would have told you to throw in the extra little curvy piece that you see right here. As far as getting the accuracy of where this would peak, in a rough sketch, from what we know right now, you really would not have come up with exactly where this peak would go. You should be able to at least ballpark it maybe in the rough sketch, but you really wouldn't know without either plugging in a bunch of x's right here and getting their y values, or using calculus, which is something we're going to do later on down the road. But so at least for now, based on what we've just talked about, we should at least be able to come up with somewhat of a decent sketch on this. Let's try a few of these for practice, and we're going to end on this. So we're going to do these three on the next page. So I have some graphs for you on the next page. So I'm going to start out with my x plus 2, x minus 1 to the third. And I hate writing in the corner right here, so I'm going to put it over here. So that was, and I knew I would forget this, x plus 2, x minus 1 to the third. Alright, so as far as the zeros go, obviously at negative 2, he is an odd power, and it's only a power of 1, so more of a linear path through negative 2, and it will cross because of the odd exponent. At positive 1, I should have a cubic function, right? So together, though, if you look at this as a whole, this is a first power, this is a third power, so total, my overall idea is x to the fourth, which means both n behaviors should be going up because it's an even power, right? So both of these should be going up. My leading term is technically a positive 1 right here, which means I know they're both going up and not both going down, right? And so let's see if we can't fit all of that through this. So this one started up, it's going to cross over the negative 2, so I know, and this is a real rough sketch, so but I'm at least giving us an idea. I'm going to make a harder line in a second. So something like this, whereas this one should be a cubic function, so more of an S shape. So if I did something like this, passing through negative 2, and then as I come back up, this one should take on more of an S shape and look something like this. I really don't know exactly where this minimum would be unless I plugged in some real numbers. I could plug in negative 1 and 0 for x and get some actual real values here, and that would make this graph more accurate. But for now, I just want us to be able to do a rough sketch similar to what we just did. Of course, you could, when appropriate, you can use a calculator to check an answer. Just make sure that we did it right. Make sure that we're on the right track. And so that we're on the right track. Obviously, that local minimum is much lower than what I did. But like I said, I would only know that if I actually plugged in some real numbers for x in this area of the graph. Let's try 2 more. So we're going to do number 15 here, which is x minus 3 squared, x minus 1 squared. So x minus 3 squared, x minus 1 squared. So again, my zeros are going to be at positive 3, positive 1. So there's our zeros. Again, these are both quadratic, so really both taking on a parabolic shape as we graph this one. Total, this is x to the fourth, which means both ends are either both up or both down. Because this is positive, I know these guys should both be up. So if they're both going to take on this quadratic parabola shape to it, and again, we also know that because it's even, it would bounce and not cross through. So I would estimate something along these lines. So there's kind of my first parabola, and then as I go to the other one, again, it's going to bounce. And so if you sort of look at them isolated, it's kind of like 2 parabolas put together, right? It's like here's a parabola and here's a parabola because they're both x squared. Okay, and so again, you could throw that into a calculator and we could be much more accurate on this if we wanted to. We could definitely plug in positive 2 to figure out this local maximum. We could also plug in 0 to get my y-intercept, and that would have been more accurate as well. Let's do one more. The last one is going to be x plus 2, x minus 3 squared. So x plus 2, x minus 3 squared. And again, always good to maybe pause the video, give this one a shot before I do it. We have 3 zeros on this one. We have 0, negative 2, positive 3. So there are our 3 intercepts total. This is a 1 plus 1 plus 2. So this is an x to the fourth type of a model, which means either both ends are up or both ends are down because it's an even power. And in this case, again, leading term positive. I guess I should have come up with some negatives in here, but that's okay. So both of these will be going up. At this 0, it should cross. It should cross, and it should bounce. Right? These will take on a little more of a linear shape because this is a first power and a first power. This one will be more of a parabolic shape because it's a quadratic. So let's see if we can put all that together. So at my -2, it should cross. At my 0, it should also cross. I could have made this probably a little more curvy. It's going to go up here. And off of this guy, it's going to bounce. And should do something like this. And again, this is more of a linear path. This is more of a linear path. And this is more of a parabolic path. Right? So it fits all those descriptions that we would expect. Of course, throw it on into the calculator. You can back up our answer that way. But that's it for this one.